So now we jump back to chapter 5, and now that we understand the behavior of gases, we can talk a bit about thermodynamics. This is just a general overview of important thermodynamics concepts. You'll actually go over this in a lot more detail next semester, and you'll talk about different types of thermodynamic functions. We're going to focus in on a function called enthalpy, which I'll explain at the end of this video, or towards the end of this video, what that is. But the interesting thing here is that whatever we learn in this chapter about how we deal with enthalpy, when you learn about other thermodynamic functions, they behave in the same way. So the mathematical skills that you develop here will translate into any aspect of thermodynamics that you run across. Okay? So that's why thermo is really important. That's why getting this general foundation is going to be essential for your chemistry progression here. Thermodynamics is sometimes abbreviated just thermo, and it translates into the motion of heat or the motion of energy, okay? So it's all about looking at what happens to energy as we make changes, and the changes that we care about are changes associated with physical processes or chemical reactions. So if we run a reaction, there may be a change in energy, and we need to quantify that because we can take advantage of that sort of thing. Before we get to reactions, let's focus back on gases in a cylinder with a piston. As this piston moves up and down, we actually can generate energy, all right? And that energy shows up in the form of work. So W stands for work. And this you learned about in physics. Work is defined as force applied through a distance. So F is a force and D is distance or displacement. So F times D is work. Gases, which is where we usually sort of build our ideas of thermodynamics because they're the simplest system because we can pretend that they don't interact, right? Gases have an interesting work formula. If you actually take this force times distance idea and apply it to gases, you get that the work done by gases is minus P delta V. Okay, now this is just a formula to know, all right? Pressure can be in atmospheres, and whenever you see a delta, that means final minus initial, all right? Final minus initial. So as the piston goes up and down, work can either enter the system, or you could generate work from the system, right? Work is sometimes negative. Right? So when would work be negative? If you look at this formula, if V final is bigger than V initial, right, then this is positive. Pressures are always positive, so this negative sign, all right, makes the work negative. So when V final is greater than V initial, we call that an expansion, and work is going to be negative. Now, if you imagine your hand here, right, and the piston's starting there, and all of a sudden the piston moves up because this volume in here got bigger. Energy would have left the system and gone into your hand. And so when you see a negative sign describing any energy, and work is definitely an energy, right? When you see a negative sign describing an energy, it means that energy is leaving the system. Work could sometimes be positive, right? Well, how could work be positive? There's this negative sign out in front, but there's also this subtraction here, right? And if V final is less than V initial, when you do that subtraction, you get a negative sign that cancels with that negative sign there, okay? When work is positive, all right, energy has entered the system. Work is a very particular type of energy, all right? And if we think about how we could make energy enter the system, well, how is V final less than V initial? That means we have to contract this. That means if your hand was here, you yourself would have to use your muscles, and you would have to put energy into the situation by pushing this piston down. The system, though, gains that energy that you put in. So whenever you see a positive quantity for any sort of energy, that tells you that energy is entering the system. And we stay focused on the system this semester. Now, as this piston goes up and down, and work is being done by the system or work is being done onto the system, as work leaves the system or goes into the system, another thing happens, right? The system, right, actually can have a Q associated with it. And Q stands for heat. And this is where we spend a lot of this chapter. Q stands for heat. So, there used to be these toys where you would like kind of flip them up and down, and there would be a noise that would be made as you flip them up and down. And that's the most kind of real world example I can think of this. If you did it really fast, what you would notice is that eventually it would start to feel hot. And that's because gas particles are on the inside of the thing that's moving, which kind of represents like a piston and a cylinder. Gas particles in the inside of that toy are rubbing up against this wall and they're generating heat. Okay? And we feel that heat based off a temperature difference from what our hand has in terms of its kinetic energy and what the cylinder has in terms of its kinetic energy. That's because heat is defined as the energy. Let me start over. Heat is defined as the energy that flows to nullify a difference in temperature. Okay? If two objects have the same temperature, then they have the same kinetic energy. You touch them, no heat flows. But if I have a hot object and a cold object and I touch them, all right, the hot object is going to get colder and the cold object is going to get hotter. And they're going to meet in the middle somewhere. Not in the middle. They're going to meet somewhere between those two temperatures. Okay? Heat flows from hot to cold. And heat keeps flowing until you have the same temperatures, until you've nullified a difference in temperature. Okay? So as this, work process occurs, right, heat also flows in or out of the system, right? Now we're going to see that we have a couple different formulas for heat, right? And a couple different ways of getting heat, because it ends up being, like I said, one of the most important thermodynamic quantities that we can focus in on in terms of importance in chemical systems. Heat, right, could have a positive sign. When heat is positive, what does that tell you? Heat is an energy. So if heat's an energy and it's positive, that tells you that energy has gone into the system. All right? When heat is positive, we say that process is endothermic. The system has gained energy in the form of heat. And we're going to see in subsequent videos that heat will have formulas, and sometimes we'll analyze those formulas and heat will be negative. Now, what does that mean? That means that energy has left the system. Energy has been released by the system in the form of heat. And for those situations, we say that those processes are exothermic, right? Heat is going away, okay? So this is what we call like a sign convention, and we went over a sign convention with work as well. But again, just focusing on the more important one for us, endothermic versus exothermic, and what it means for the things that we care about, like chemical reactions, okay, is essential. It's super important to understand. Endo means positive heat, means that energy is going into the system. Exo means negative heat, which means that energy is going out of the system in the form of heat. Right? All energies that we talk about, such as heat and work, have units of joules or kilojoules. Okay? And so because we're introducing units, there's a couple unit conversions that you need to be aware of. Right? 1 liter atmosphere is 101.325 joules. Right? So our work formula has a P delta V. So it has an atmospheres times a liters. Well, this is how you take that and bring it into, all right, a common unit for energy, joules or kilojoules, all right? Sometimes we measure energies in cals, but we need to get back to joules because that's going to be the important relationship that we really kind of focus in on, all right? So 4.184 joules is equal to 1 cal. And even though we won't really use this much this semester, if at all, okay, I'm going to introduce this. Where have you seen a liter atmosphere before? You've seen it in R, okay? So in our gas constant, we used to have 0.08206 liter atmospheres per mole Kelvin. That actually means there's two different versions of R. And even though this becomes more important next semester, I'd be remiss not to introduce it. This is what we're going to refer to as the energy R. It's the same R, but essentially you just changed liter atmospheres to joules with that conversion factor. Okay. So with this quick little introduction into the important energies that we care about and the sign convention associated with those energies, right? We have one more intrinsic thermodynamic quantity that matters to us in chemistry this semester. And that is a quantity we call enthalpy. Now, enthalpy is an energy. So that means it has units of joules or kilojoules. Okay, so this is an energy. What is it specifically, though? What is the definition of enthalpy? Enthalpy is the heat. Is the heat that flows when the pressure is constant. All right? It's the heat that flows when the pressure is constant. Now, why is this so important for us as chemists? Well, we already know that heat's important to us, and enthalpy is equivalent to heat if the pressure is constant, right? Now, if the pressure is constant, we call those situations isobaric. And you might have heard of like isobars on maps, like regions that have the same pressure. A constant pressure means that it's isobaric, right? The process is isobaric. Most reactions that we do in the laboratory are done open to the atmosphere. They're done in a constant pressure environment. So most of the reactions that we end up doing, all right, when we measure their heat, because the pressure is being held constant, it really means that we're measuring the enthalpy, okay? So it's just the most common form of heat we see. Heat can take on different forms, and that's, we have whole courses devoted to thermodynamics, and in this course we get one chapter. So there is this kind of fuzziness associated with this rebranding of heat to enthalpy, but it's important to know that it is a rebranding, and enthalpy is heat as long as the pressure is constant, but that happens so many times in reactions that we start to use these words synonymously, all right? So Q is equal to the enthalpy, which is given the symbol delta H, right? This is only ever true if you have an isobaric situation, but again, one more time, that's incredibly common to us as chemists. Reactions then have an enthalpy. All right? Reactions often have a delta H associated with them. Okay? And so what you'll see for a reaction is reactants and products written like you would normally see. And then aside of that reaction, you'll see a delta H with some number and joules or kilojoules. Right? We call this setup, right, that shows not only a reaction, but its associated heat, its associated enthalpy. We call this a thermochemical reaction. All right, thermochemical reaction. It contains both energy information and reaction information all in one spot. And to preview next video, now that we have everything introduced, when you have a thermochemical reaction, the new thing that we learn that meshes with the old stuff is we can build mole to energy bridges. remember, heat is energy, is enthalpy for these situations. We see that enthalpy has units associated with being and energy. And so the interesting thing here is anything we could do with a thought process that generated a mole to mole bridge, right? Let's just remind you, say we have 2A going to, or 2A plus B is C, right? So we know we could write 2 moles of A is equal to 1 mole of B, and we can build a mole to mole bridge. When you have a thermochemical reaction, right? What this tells you, and let me just put a number here like 5, just so you can kind of see. In the context of this thermochemical reaction, we can build a mole to energy bridge. This setup tells me that 2 mole of A is equal to 5 kilojoules. And 1 mole of B is equal to 5 kilojoules. All right? Just like we can use the stoichiometric coefficients to build mole to mole bridges, now when this delta H is written aside of it, all right, 1 mole of C as written is 5 kilojoules. All right, we can build these mole to energy bridges, and we can get energetic information about our reaction. And it's an incredibly important tool. And next time we'll start with examples associated with that. The other thing that we can get, and it'll be the last topic I talk about right now, all right, for this video. What does it mean that this delta H is positive? The other thing a thermochemical reaction tells us is whether the reaction takes in energy to run or whether the reaction releases energy to run. And remember, delta H is a heat. So what does a positive heat mean? For this example, it tells you that we have an endothermic reaction. And so this reaction, it actually requires energy to run, right? If we had a different example and this was negative, right? And we'll see those next time, all right? But if we had a different example and this was negative, it would be exothermic, and you would run this reaction and it would generate energy, right? And an important example of that is like a combustion reaction where we burn something and we get energy. And why is that? Because its delta H is negative. Opposite what we see here with a positive delta H. Okay. So there is a lot of sort of fuzziness usually associated with understanding these concepts the first time. So do your best to organize your thoughts associated with them. And what we'll get into with the subsequent videos is how we use these ideas and we actually do calculations. I just introduced a very important idea, mole to energy bridge, but I'm going to show you next time exactly how we can use that in problems, what exactly you'll see in wording that tells you that you know you need to invoke a mole to energy bridge. And then what you'll find with that first section is it'll feel really familiar and we'll be using skills that we used before and that you've perfected already. Okay, so even though things still seem fuzzy, I always like to remind you guys to stay confident, and you'll be able to get this with just a little bit of practice and getting some help from me as needed. Okay, so next time we'll be using these mole to energy bridges to do calculations.